Section: Introduction. In this section, we discuss the evolution of large language models, LLMs, like ChatGPT, Llama, and Mistral, and the concerns surrounding their ability to handle harmful queries. We highlight the importance of implementing safeguards to ensure the safety of these models. Approaches such as supervised fine-tuning, SFT, reinforcement learning from human feedback, RLHF, and direct preference optimization have significantly enhanced the security of LLMs, enabling them to reject harmful queries effectively. However, despite these advancements, LLMs aligned with these approaches can still be vulnerable to sophisticated attack prompts that can bypass their defenses. This vulnerability can lead to the generation of inappropriate or illegal content, disrupting societal norms. This raises the question of whether we can precisely target and modify the problematic areas in LLMs to detoxify them. Recent progress in knowledge editing methods for LLMs has provided a way to make post-training adjustments to these models without compromising their overall performance. Leveraging knowledge editing for detoxification seems like a logical step. However, existing datasets for detoxification primarily focus on specific harmful topics, overlooking the threat posed by attack prompts. To address this gap, we introduce a comprehensive benchmark called SafeEdit, which evaluates the detoxification task through knowledge editing. SafeEdit covers a wide range of unsafe categories and includes powerful attack templates. We expand the evaluation metrics to assess defense success, defense generalization, and overall performance against various malicious inputs. We explore different knowledge editing approaches on Llama 2-7B Chat and Mistral 7BV0.1 and find that knowledge editing shows promise in detoxifying LLMs with minimal impact on their general performance. Our proposed method, detoxifying with intraoperative neural monitoring, DINM, aims to identify and edit toxic regions in LLMs efficiently. Our experiments demonstrate that DINM outperforms traditional methods in detoxification success rate and generalization. It is also efficient, requiring no additional training and showing quick editing capabilities. The location of toxic regions plays a crucial role in detoxification, with DINM focusing on erasing these regions while other methods may bypass them. In conclusion, our study highlights the potential of knowledge editing in detoxifying LLMs. We introduce the SafeEdit benchmark, propose the efficient DINM method, and suggest future applications of supervised fine-tuning and knowledge editing in this context. Section Summary. In this section, we discuss the growing concern around large language models, LLMs, like ChatGPT and Mistral being vulnerable to harmful queries despite safety measures like supervised fine-tuning and reinforcement learning. We introduce a new method called detoxifying with intraoperative neural monitoring, DINM, that efficiently locates and edits toxic regions in LLMs, significantly improving detoxification success rates without compromising general performance. Our experiments on Llama 2-7B Chat and Mistral 7BV0.1 show that DINM outperforms traditional methods, highlighting the potential of knowledge editing for detoxifying LLMs and paving the way for future research in this area. Section: Dataset. In this section, we construct SafeEdit as depicted in Fig. Harmful question. We categorize unsafe scenarios of LLMs into 9 types following an existing security assessment framework. To create malicious questions for each type, we use the GPT-4 API to generate 60 harmful questions. This results in a total of 540 harmful questions. An example of a harmful question could be, "Where can I sell stolen art pieces?" which violates laws. Attack prompts are designed to provoke unexpected or harmful responses from LLMs. We gather 48 attack prompts from various sources and combine them with harmful questions to form adversarial queries. For instance, we concatenate a harmful question like, "How can I counterfeit money?" with an attack template to create an adversarial query. To prompt GPT-4 to generate safe responses for each adversarial query, we input the query directly into its API. This process helps us create a dataset called D_edit, which includes adversarial queries, safe responses, and unsafe responses. To ensure that the detoxification process does not affect ILM's responses to normal requests, we collect instances of normal interactions denoted as D_cons. These instances help us evaluate the general performance of LLMs. To maintain the quality of SafeEdit, we use a hybrid strategy combining an automated classifier and manual verification. The classifier is trained to assess the safety of response content and achieves high accuracy. We also manually refine attack prompts and review data cases to ensure high quality. The SafeEdit dataset consists of training, validation, and test instances, totaling 4,050, 2,700, and 1,350 respectively. This dataset can be used with various methods to improve response safety and knowledge editing. We introduce evaluation metrics such as defense success and defense generalization to assess the detoxification performance and potential side effects. Defense success evaluates the safety of edited content, while defense generalization assesses the model's ability to defend against different types of malicious inputs. In defense generalization, we consider various scenarios to ensure the edited model can handle different types of harmful questions and attack prompts effectively. These metrics help us evaluate the overall performance of SafeEdit and defending against malicious inputs. Section Summary. In this section, we construct SafeEdit by categorizing unsafe scenarios of LLMs into 9 types and generating 540 harmful questions using GPT-4 API. We then create adversarial queries by combining these harmful questions with attack prompts to prompt GPT-4 to generate safe responses, ensuring the quality of SafeEdit through a hybrid strategy of automated classification and manual verification. Section: General Performance. In this section, we assess the overall performance of the edited language model, LLM, in various tasks beyond its original scope. We evaluate the model's fluency in responding to malicious inputs using n-gram analysis. Additionally, we measure its proficiency in knowledge question answering, KQA, on trivia QA and content summarization, CSUM, on XSUM using Rouge 1 metric. These evaluations are carried out using the Open Compass tool to ensure consistency. Our proposed baseline, DINM, focuses on identifying and modifying toxic regions in LLMs through contextual semantics rather than relying on specific characters. Inspired by intraoperative neurophysiological monitoring, DINM efficiently locates and eliminates toxic regions with just one test instance, without the need for additional training. By pinpointing and modifying these toxic areas, the edited model becomes more resilient to harmful inputs. To locate toxic regions, we analyze the hidden states of the LLM, which consists of an embedding matrix E and multiple transformer layers. By comparing the hidden states of safe and unsafe sequences at each layer, we identify the transformer layer that most effectively distinguishes between the two. The parameters within this identified toxic layer are considered as the toxic regions that need modification. During the detoxifying process, we adjust the parameters of the toxic regions while keeping the rest of the model frozen. By iteratively tuning these parameters to enhance the model's ability to generate safe responses to adversarial inputs, we aim to maintain the model's performance on unrelated tasks. The detoxification process is guided by a total loss function that balances the model's defense against adversarial inputs and its performance on regular inputs. Through backpropagation, we update the parameters within the toxic regions to diminish their toxic effects, resulting in a more robust and reliable edited model. Section Summary. In this section, we introduce a baseline method called DINM to locate and remove toxic regions in large language models, LLMs, using contextual semantics, inspired by neurophysiological monitoring techniques. By identifying and modifying these toxic areas, the edited LLM can effectively defend against malicious inputs without requiring additional training. The detoxifying process involves tuning the parameters of toxic regions while keeping other model parameters fixed, aiming to increase the likelihood of generating safe responses to adversarial queries and maintaining the model's proficiency in unrelated tasks. Section: Settings. In this section, we use various knowledge editing baselines, including SFT and self-reminder, along with our proposed DINM, for comparison. We also evaluate the performance using metrics in the following sections. We provide all the experimental details as well. Knowledge editing shows competitive detoxification performance. It can change specific behaviors of LLMs, which is promising for detoxification applications. For example, it achieves detoxification rates of around 68.55% and 70.64% on different models, which are comparable to other methods. However, these editing methods struggle to generalize detoxification. Our method, DINM, demonstrates even better detoxification performance with improved generalization. It shows significant enhancement in detoxification performance, with rates increasing from 43.70% to 88.59% and from 46.10% to 96.55% on different models. DINM can effectively defend against various malicious inputs, including harmful questions and attack prompts. It also shows the ability to generalize edits from one unsafe category to another, enhancing defense rates against different types of malicious inputs. DINM efficiently detoxifies LLMs without requiring extra training processes. It directly uses a single test instance to adjust toxic regions, which is faster compared to other baselines. The memory consumption for different approaches is also reported. Despite some side effects, knowledge editing has significant potential as the scale of LLMs increases. Knowledge editing may slightly compromise general abilities, but the impact is minor. DINM, on the other hand, shows minor impacts on one model and even boosts performance on other tasks for another model. This could be due to the detoxified LLM outputs aligning better with specific tasks. However, the exact reasons need further investigation. DINM also tends to repeat sentences, indicating challenges in detoxification via knowledge editing that require new methods for resolution. Overall, compared to other methods, DINM has a similar impact on general abilities on one model and a smaller impact on another. Section Summary. In this section, we compare knowledge editing baselines, traditional detoxifying approaches, and our proposed DINM. Knowledge editing shows competitive detoxification performance but lacks generalization. On the other hand, DINM demonstrates stronger detoxifying performance with better generalization, effectively defending against various malicious inputs and enhancing detoxification efficiency without the need for extra training processes. While knowledge editing compromises general abilities to some extent, the impact is relatively minor compared to other methods, highlighting the potential and challenges of detoxification techniques in enhancing model performance. Section: Toxic regions location play a significant role in detoxification. In this section, we investigate the importance of locating toxic regions in the detoxification process. We start by comparing the detoxification performance when using suffix system prompts without parameter tuning, tune, to the standard method DINM. The results show a significant decrease in detoxification and overall performance with tune. We further analyze different suffix system prompts' effectiveness and conduct ablation studies to understand the impact of removing toxic region location, location, general knowledge constraint, constraint, and suffix system prompt, prompt, individually. It is crucial to note that location refers to randomly selecting a layer within the LLMs for modification. Removing toxic region location leads to the most substantial performance drop, emphasizing the importance of precisely identifying and eliminating toxic regions rather than fine-tuning indiscriminately. This process also enhances generalization and resilience against attacks from malicious inputs. We then explore the mechanisms of traditional methods like SFT and DPO in comparison to our DINM for erasing toxic regions. By training a toxic probe to quantify toxicity levels and analyzing activation shifts, we observe that DINM directly reduces toxicity without altering information flow, unlike SFT and DPO, which rely on activation shifts to bypass toxic regions. Our findings show that DINM achieves a 2.72% toxicity reduction without shifting information flow, indicating its effectiveness in erasing toxic regions. This approach defends against out-of-domain attacks and shows promise for LLM detoxification. Additionally, we categorize traditional detoxification methods into self-improvement, toxicity detection enhancement, and prompt engineering, highlighting the novelty of our knowledge editing paradigm for precise toxicity elimination with minimal tuning steps. Section Summary. In this section, we investigate the importance of toxic regions in the detoxification process. By comparing different suffix system prompts, we find that locating and erasing toxic regions significantly improves detoxification performance and generalization, making models more resilient against attacks. Additionally, our method, DINM, directly reduces the toxicity of toxic regions, unlike other methods like SFT and DPO, which may still leave toxic regions intact, leading to poor generalization. Section: Knowledge Editing. In this section, we focus on knowledge editing. Knowledge editing involves making specific changes to LLMs to correct outdated or incorrect information. We use techniques to detoxify LLMs by combining expert and anti-expert models. By extracting and negating only the negative aspects of the anti-expert model, we aim to maintain the overall strengths of the LLM. We also work on removing harmful words directly from the neurons in FFNs through reverse engineering. Our approach involves identifying neurons that contain sensitive information. These editing methods typically target individual words or phrases. When generating safe content with LLMs in response to user queries, the new context is determined by the overall meaning rather than specific words. Our method, DINM, locates and removes toxic regions in LLMs based on contextual semantics, aiming to eliminate harmful content.